Time travel debugging, but for keys. Time-based key value store is a Pattern Mastery 100 favorite because it blends hash maps with binary search. It's asked at Meta/Amazon to see if you can store version data and pull the value as of a timestamp, fast. Today we'll lock it down with basic and produce clean O-login. Lookups. We must design a class with set key, value, timestamp. Store the value for the key at timestamp. Get key, timestamp. Return the value for the key with the largest timestamp less than or equal to given timestamp, return if none. Input guarantee. For each key, timestamps in set are non-decreasing. That means we can keep a sorted list per key. Naively scanning backwards at get is on and too slow. Because per key timestamps are sorted, we can binary search the last timestamp not exceeding the query, O-log_n, time. We'll store dict key, list of, timestamp, value, or two parallel lists, append on set, and use bisect_right on get. Keep store. Dict str, list tuple int, str. Set, store key. Append timestamp, value. Get, binary search that list to find the rightmost pair with t less than or equal to query. If none, return. Now let's solve solution 1, the binary search with bisect approach. Time complexity. Set operation is O1. Get operation is O-log_n. The idea: each key stores a list of timestamp, value, pairs. Every time we set a value, we just append it, super fast, O1. For get timestamp, we need to find the latest timestamp that is less than or equal to the given timestamp. Instead of scanning the list, we use binary search, bisect_right, which finds this position efficiently in logarithmic time. Line-by-line explanation of the code. We import Python's built-in bisect module. This gives us fast binary search tools. Think of it like asking Python to help us quickly find where something belongs inside a sorted list. We start a new class called TimeMap. This class will hold all our timestamp data. This initializes the object every time we create a time map. We create a dictionary called store. Each key in this dictionary will map to a list of timestamp, value, pairs. Basically, key maps to a timeline of values. This method saves a value together with its timestamp. If this is the first time we've seen this key, we create a new empty list for it. We simply add the timestamp value pair to the end of the list. No sorting needed, timestamps are always increasing. This makes set O1. This method retrieves the value associated with the largest timestamp that is less than or equal to the given timestamp. If the key does not exist at all, we return an empty string. We grab the list of timestamp, value, pairs for this key. This is the heart of the algorithm. We ask Python where the pair, timestamp, something very large, would be inserted. By using CHR127, a very large ASCII character, we make sure our search finds the rightmost spot for this timestamp. Binary search makes this step O-log_n. If the result index I is 0, it means every timestamp we have is greater than the requested one, so there's no valid value to return. Otherwise, we return the value attached to the timestamp just before index I. This gives us the correct value for the latest timestamp less than or equal to the requested timestamp. And that's how this algorithm works. It first organizes timestamps in simple lists, then uses binary search to instantly find the closest valid timestamp. Efficient, simple, and elegant. Set is O1 because we only append. Get uses binary search, making it O-log_n. Using timestamp, CHR127, ensures we get the correct boundary using bisect_right. Each key maintains its own timeline. Now that we've implemented our TimeMap class, let's verify that it behaves correctly with a sequence of operations. This test will show how we can store key value pairs at different timestamps and retrieve the most recent value for a given time. We'll walk through the input operations, see how values are recorded and retrieved, and confirm that the output matches the expected results. Let's test our time map using this input. We perform a sequence of operations. Initialize a time map. Set key foo to bar at timestamp 1. Retrieve the value of foo at timestamps 1 and 3. Set key foo to bar 2 at timestamp 4. Retrieve foo at timestamps 4 and 5. Here's why the solution works. The algorithm stores all values of each key as a list of timestamp value pairs. When get is called, it finds the largest timestamp less than or equal to the requested timestamp using a binary search. Step by step, after set foo, bar, 1, the list for foo is 1, bar. Get foo, 1, returns bar because timestamp 1 exists. Get foo, 3, returns bar because the latest timestamp less than or equal to 3 is 1. Set foo, bar 2, 4, adds the pair, 4, bar 2. Get foo, 4, returns bar 2, and get foo, 5, also returns bar 2 as the most recent value less than or equal to 5. And that is exactly what the program outputs. Null, null, bar, bar, null, bar 2, bar 2, bar 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully handles timestamped key value storage and retrieval, efficient, accurate, and reliable. Our implementation is correct. It accurately stores multiple values per key with timestamps. It retrieves the latest value less than or equal to the requested timestamp using binary search. It passes the given test case and is efficient for larger inputs. This is solution 2, implementing a time map using manual binary search to efficiently get values by timestamp. Instead of relying on Python's bisect, we perform a classic binary search to find the largest timestamp that is less than or equal to the target. Time complexity is O log n, per get operation, where n is the number of timestamps for a given key. Each set operation is O1 since we just append. Binary search lets us quickly find the correct value. We define a class time map to hold our key value time data structure. Initialize an empty dictionary to store all key value pairs as lists of timestamp, value, pairs. For a given key, append the timestamp, value, pair. If the key is new, create an empty list first. To get a value at a given timestamp, check if the key exists. If not, return an empty string. Otherwise, get the list of stored pairs for that key. Set up left and right pointers for binary search, and initialize a variable to hold the result. While the search space isn't empty, compute the middle index. If the middle timestamp is less than or equal to the target, save its value and search the right half to find a later timestamp. Otherwise, search the left half. Return the value associated with the largest timestamp less than or equal to the target. If none exists, return an empty string. Binary search ensures O log n, per get. Set operations are O1. This works even if timestamps are non-consecutive. Manual binary search is helpful if you want more control than using bisect. And that's how solution 2 works. It first sets up the dictionary of timestamped values, then uses binary search to efficiently get the most recent valid value. Simple, efficient, and precise. This is the time map, storing values with timestamps. Set saves a value, get retrieves the latest value at or before a timestamp. Like solution 1, we track boundaries, here, timestamps, to get the correct value efficiently. For key foo, timestamp 1 bar, timestamp 4 bar 2. Get at 3 returns bar, the latest before 3. Output, null, null, bar, bar, null, bar 2, bar 2. Shows it works. Simple, accurate, and reliable. Breakdown recap. We needed to design a class with 2 main operations, set, which stores a key value pair with a timestamp, and get, which retrieves the most recent value at or before a given timestamp. If there's no valid timestamp for that key, we simply return an empty string. Assess recap. A naive way would be to scan backward through all stored timestamps each time we call get, but that's too slow. Since timestamps for each key are always added in non-decreasing order, we realized we could use binary search to find the correct version efficiently. That gives us a clean O log n lookup instead of ON. Structure recap. We stored all data in a dictionary that maps each key to a list of pairs, each pair containing a timestamp and its corresponding value. When setting a value, we just append it to that list. When getting, we perform a binary search to locate the rightmost timestamp less than or equal to the query time and return its value. Implement recap. After implementing the class with set and get methods, we ran it on LeetCode, and it executed smoothly without any errors. Check recap. We tested multiple scenarios, overlapping timestamps, missing keys, and boundary cases, and all produced the correct outputs. The main takeaway? Time-based storage problems reward structure and search efficiency. By pairing hash maps with binary search, we built a clean, scalable solution that handles version lookups in logarithmic time.